observe, if you look at proton-proton scattering, is that proton scattering is like what I just showed about the electron muon or muon-proton scattering, except it's now sort of squared, because now you have the two protons coming in, and they're like bags with some momentum in, and you get one hardish bit of one hitting a slightly softer bit of the other, so you sort of have quite a lot of soft collisions. Well, the squared number of 10 to the 10, probably. I haven't looked at this number, so I don't know. It's been a long time since I did this stuff. But you have much more soft. You have much more fragmentation. You have many more particles. What's called multiplicity. What you do is you trigger. So what you do is you choose only those events where the proton hit another one hard. So quite a bit of this proton hit quite a lot of that proton, and these things tend to come out perpendicular to the beams coming in. So what you do is you throw everything away that's all that wimpy stuff, and you only ever even look at stuff which had some sort of hard collision. Now, if you do that, and that's what we also did, then what you observe is that at medium energies, at ISR energies, we observed that what came out was stuff that looked as though it was either two jets of particles, so it was sort of a concentrated 20 or 30 different particles, which then decayed down, going in one direction, which was balanced by a whole set of particles going in the other direction, all sorts of stuff at very high energy. So that was as though something had hit something else and then bounced off and then fragmented. You should see two jets. But we didn't just see two jets, we also saw three. So you had to think there was some initial, that's a bit funny, because if two hard things have hit one another, you really should just get doing, they've come off. And so that didn't really kind of fit the quark parton model really either. But okay, you could have hard fragmentation, you had three jet events. I believe, although I don't know, I stopped looking at this stuff because it depresses me. I believe now the number of jets is much larger, and what you get is, but the idea is that if you have a struck quark and it begins to come off, the problem was nobody ever observed a quark or a gluon, so the things were somehow stuck inside the proton. So the idea that people made up, and remember, all theories are just stuff that you make up. They're just speculations. So the speculation was that you had this thing called asymptotic freedom, which is that the force between two quarks or intermediate by gluons went to very low when they were close to one another. You try to pull them apart, they generated lots of other sticky glue between them, which made the force get bigger and bigger. But if that was the case, it's called a non-abelian gauge theory as opposed to an abelian gauge theory like Maxwell's equations. So there are names for this kind of thing where the carrier of the force, the gluon, interacts also with itself. So in that case, you have fragmentation functions for these things. So you put in a probability, essentially, that something goes to another kind of quark, or it goes to a quark and a gluon, or whatever. You stick these things into a Monte Carlo, which is then called a quantum chromodynamics QCD Monte Carlo. You then tweak the parameters in this QCD Monte Carlo, which was one of my jobs. So you sort of stick these things in and generate real data. Well, no, you don't generate, you get real data and then compare it against the simulated data, which you've used using these fragmentation things. But this fragmentation stuff is made up on the basis of a model that that's actually what's happening. And the fact that you're hitting just quarks inside a nucleon is not what's supported by the data. It looks much more complicated than that. Moreover, as you go to higher and higher energies, it turns out that what's called the valence quark fraction of the proton, you can imagine that the proton was 100% valence quark. Valence quarks are the up down in the proton, up down down in the neutron. They're the ones that determine the charge of the quark and its spin, because in the theory, although the spin is messed up in the theory. O'Fallon et al. 1977, Krish, as I just said, May 1979, disproves that aspect of the quark model. And this is 1970s, for crying out loud. I mean, when are we? This is 50 years ago, 40 years ago, sorry, I can't count. And it's sitting there like a toad on top of all of this stuff, unexplained. I hate it. So this is why I say that really no progress has been made in science since then. And okay, so the idea is that in I'm just describing quantum chromodynamics to you now, Pete. I don't know if you want that, because I think it's all bullshit, right? So I'm just describing some bullshit that other people have made up, right? So they could better describe it to you if you wanted to hear it from them. But anyway, but there we go. So I'm just teaching you what's in the textbooks I read back in 1970s, right? which is still in the same textbooks, ninth
I
edition
know
or whatever.
Coupling constant for chromodynamics is makes it very hard to understand.
But it's hard to understand because it's designed, because it is hard to understand. But,
The
all
finite
sorts,
diagrams get really unmanageable.
yeah, but look, the Tao Te Ching is the oldest book in the world. Is hard to understand. It says the only. So if you read that, it's all in riddles. So hey, people can make up stuff that other people can't understand. That's no trick. I can make up lots of things that other people can't understand. But many of you may think that that's exactly what I do. but making stuff up that other people can't understand is easy.
So using your model, shouldn't it be possible to create three quarks by using a high enough pair of photons and having them end up in that same configuration?
Pete, it should be possible to catalyze the creation of matter using just light and electricity. And Arnie might want to share a nice little video of you where it shows people doing exactly that. But you should be able to do far more spectacular things than just that. You should be able to engineer new kinds of power source. So, and people are doing it without my help, which is pretty impressive. There it is, Sapphire. This is going to change the world if this thing's true. I mean, if it isn't a hoax, there's only two possibilities. Either it is or it isn't a hoax here. If it isn't a hoax, this is going to completely transform the world. It's a catalyzation of matter transformation. It's matter transmutation. It's changing one kind. It's actually, I think they're doing matter creation, and I think they need to be a bit careful. If you guys are listening, there's something else happening here which you're not aware of, and you probably need to talk to me because it could be dangerous for your health. So please do get in touch. So, but I think I know what's happening in those systems, and my theory does explain exactly how that's working. Not just that it's working, but how it's working. Now, as for the quark fragmentation, all that stuff, do I really want to explain what's happening at a trigger level of 1 in 10 to the 10? A very, very rare events, which are highly selected to be exactly the kind of thing that would show those hard scattering going on between protons? No, because that's never going to be anything that's useful for engineering. It's never going to be anything.
The three quarks are formed by two photons, right?
I think the symmetry is formed by having confined light, and that what one's doing is one's scattering off a system, and this is supported by experiment, a system which is half mass-like and half light-like, both for the electron and for the hadrons. Now, what that would mean, for example, is that the total amount of form momentum that you integrate into the integral form momentum carried by the hard bits inside the proton should be exactly a half. Now, that is exactly what's observed. So there are aspects of what we observe in high-energy physics that are precisely reproduced by my model. If you want to know if my model exactly reproduces what people have made up for quantum chromodynamics, no, it doesn't. But on the other hand, quantum chromodynamics doesn't properly describe the experiment, so what?
About your model being so consistent with the experiments that you actually predict that you can produce the three quarks or a proton from two high energy photons.
The thing is that you can't produce a quark from two high energy photons.
No,
you have to produce this symmetry in threes of the same sort or pair anti-pair. You need three quarks or quark bar in terms of talking about quark parton model. But quarks don't exist. There is no such thing. The quark symmetry exists, but it doesn't exist as a physical particle. It's just an element of a continuous particle, which requires for its particle-ness to go around in a continuous path. And it's the requirement for going around in a continuous three-dimensional path that gives you the quark symmetry SU3. SU3 is related to a higher dimensional spherical symmetry. It's a double covering of SO4.
So just like pair production of an electron, you should have pair production of protons and antiprotons.
Oh, you do? Yeah, you do. You have pair production of muons, tauons, protons, neutrons, cascade particles, J psi's, everything. So all of them are observed. And also the reverse process. If you want to play with these sort of things, I was looking at it the other day. Also the reverse process. What does stuff decay to? So if you look at a W and Z boson, I was looking at the other day, 1/3 decays to leptons and 2/3 decay to hadrons. So they're very, very specific fractions which are tremendously beautiful that these particles decay into. But remember, the process always goes both ways. If something decays into something, then provided you could line it up, and the engineering of that might be a bit tricky, you could run the process forwards or backwards in time because it's just a reversible process. So if you want to look at what makes stuff, you're better off looking at what it turns back into because that's more defined, because you know what you started with then. So, and these are beautiful. The experimental work at CERN is utterly spectacularly gorgeous. And there's an awful lot of it. It's also free, you know, it's all open source. This is science as it should be. But the theory is messed up. Well, the theory is just not describing things properly, that's all. But it's hard to do this. I mean, it's not that anybody's doing anything bad or wrong. It's just that extending quantum mechanics, understanding how much stuff works, is actually very, very difficult. So, and really it was something I tried in my youth. And I tried pretty hard in my youth to do this, but it just wasn't capable of doing it. It's only when I met Martin that the two of us working together could begin to make any kind of impression on this problem, which we did over decades, I think. So, that's often been the case, that people have said, yeah, okay, we know the standard model's just a model, and you keep calling my model a model, but it's not now, it's a theory. It's a theory which starts from space and time and root energy, then ends up with a set of equations of motion for everything. That's not a model, that's a theory. But the standard model is a model, and it always has been. It's a collection of bits. And it's supposed to consist of, I mean, if you want to have a laugh, and Alex Anziker gave a talk, I think in Prague, I picked up somewhere. I must see if I can find it. I must ask him if we can host it, because it really is hilarious. Although I can see that he'd have trouble with, and I will too, because my knowledge of high-energy physics and elementary particle physics and gauge theories is probably well out of date by now. This is stuff I learned when I was an undergrad or beginning of postgrad. But if you look at it through with my quantum electrodynamics hat on and my group gauge theory hat on, I can see that he's making stuff that they would mock. But that's not fair, because his stuff is better than their stuff, I think. So, and the same is probably true of me. People say, no, Williams doesn't really get gauge theories anymore. You know, in the 21st century, we've gone way beyond that. But I don't care about that. I'm just going to do my stuff and try and do it well. So, and because I think it's what needs doing. So
far, your model seems much simpler than anything I've seen that they're trying to do with the standard model.
Well, I think the problem with the standard model stuff is people are just making stuff up. You know, the stuff that's been made up is getting more and more ridiculous. I mean, this idea that a force gets bigger as you pull things apart, and then you have to have, if you're trying to describe that as being a particle exchange, those particles in their exchange have to interact with one another. Okay, brilliant idea, but you're getting to something, but then you can't find these particles, you can't detect them, you can't see them. That should be a bit of a red flag to saying you're maybe not on the right course here, guys. And this is the reason that I gave up my shining career in high-energy physics and just decided to jump out and do engineering, because that seemed to me to be a complete and utter waste of time, spending life doing that. And I wasn't the only one, there were people who did the same. So, but lots of my friends remained, of course, and continued to work on that, made a career out of it. But I don't think they're particularly happy about it necessarily in terms of the science. But that's me projecting on.
I forwarded your papers to a number of physicists, but I couldn't get any of them to argue anything being wrong with your papers.
No, they can't. And if they want to, feel free. I'm open to talking to you about it. You tell me where I'm wrong. Go for it. That's what science is about.
Right. It's kind of frustrating that there's no one willing to argue with you what's wrong with your theory.
Pete, people will argue with me. I was at a high-energy physics conference. Somebody came over and argued with me. and
Oh.
he was a big guy. He's about 6'6". So he sort of stood over me and sort of looked down at me, and he started arguing with me the standard arguments. And to his utter astonishment, he lost in about 3 minutes, less than it took the time for the Big Bang of the universe. And he kept losing. He kept coming up with standard arguments, but I know all of them, so I'm not impressed. And he just began to get more and more angry. I thought he was going to hit me, but he lost comprehensively and rapidly and simply. So yeah. So if they want to argue, this is why I'm not getting stuff published. I think my stuff has got a bit too much maths in it. It looks a bit too much like science. I mean, okay, if people are crazy and sort of come up with crazy ideas as to everything's infinite energy and some derivative of that, or many worlds, or all that sort of thing, that's all tolerated. But when it actually starts getting serious, this is a bit scary for some of these guys. So we'll see what happens, though, as this project develops. We'll see what happens. Survival of the fittest. It's all Darwinian selection. We'll see which one survives.
John, that's probably a good stopping point, no?
Yeah, let's stop it. Hey. Good. Okay, it's probably